All right, let's go ahead and get started. It's 2 o'clock. So thank you for turning in your homework. New homework assignment is up on Blackboard, so take a look at that. I know I got a lot of emails last night that people were asking for help on problem number 1, and I didn't know if that's because they left that to the end or if they were just starting the homework. I don't recommend you wait till the night before because some of these problems can take a little thought and may need a little bit of assistance. So I may or may not be answering emails at 9 p.m. on Monday night, the day before the homework is due, so don't count on that. It's better to get in touch earlier. And again, I always have office hours before class, so if you have questions and you need help on homework, then come see me. And our exam is coming up on September 21st, so it's a week from Thursday is our first exam, and it will cover chapters 1 through 9. It's comprehensive just because the class is comprehensive. So there's no way of getting around the material in chapter 1 because it's all inclusive. Yes?
Is it 1 through 9 of stuff that we covered in Thermo 2?
Well, the stuff that we've covered in Thermo 2 builds upon the stuff we covered in Thermo 1. So the problems are going to be more difficult than were in Thermo 2 just because we have additional layers now added. If that makes sense. So it's going to include things you learned in Thermo 1, but that's because you're using those things now in Thermo 2. Any other questions? We'll talk more about the exam. A week from today is a review day. So I plan to do a lot of examples, have you do some group work, work on problems together, and practice that problem-solving process so that you can get a little bit more practice for the exam, which of course you don't work on in groups on the exam. You have to do it by yourself. So knowing how to start these problems and independently solve them is very important because that's how it is on the exam. Okay, so today we're moving on through our power cycles. We're now talking about diesel, Stirling, and Ericsson cycles. So we'll spend the majority of the time actually talking about the diesel cycle because we do a lot more analysis on that, and then we'll also talk about Stirling and Ericsson, as well as some other interesting things that have come up as I've studied and you've studied, and students have sent me things about kind of interesting concept cars or engines that are in production or proposed to be in production. So we'll talk a little bit about that as well because it's kind of interesting. So just to review, there are 2 types of reciprocating engines that we study in this chapter. The first is a spark ignition. So this is how gasoline vehicles are, how the combustion process occurs. So there's a spark that ignites the fuel. Whereas compression ignition, we rely upon the ignition temperature of the fuel to self-ignite. So we compress the gas above that temperature, and then we have ignition, which forces the piston down, and that's your power cycle. So that's how you get any work out of a vehicle, is through the piston being forced down by combustion. So internal combustion engines, that's the primary methodology of workout, and there's 2 different ways that it's delivered. There's actually many different in between. We'll talk about that later in the lesson, but if we're categorizing them as spark ignition and compression ignition. And the timing of that is very important, because if you notice, we have 4 different cylinders in this particular case firing, and they're not all firing at the same time. And they're not all firing in a line. They have a very specific timing which is meant to reduce vibration in the engine as well as deliver the maximum power output. So if we were to fire the cylinders 1, 2, 3, 4, we would get almost like an oscillating or a galloping motion within our engine. So they need to kind of alternate and not be in succession, although the timing of them is consistent for every piston cycle. The length of time that it takes for each piston to move up and down is the same. They're just not all firing at the same time and not all firing in a row. So the diesel cycle is very similar to the Otto cycle or the gas cycle in that it consists of 4 strokes. We have a compression stroke where air in our cylinder is compressed. Then there's the power stroke where the fuel's injected and it self-ignites and forces that piston down, so that's what gives us our power output. The exhaust stroke where the piston moves back up and these byproducts of combustion are exhausted, and the intake stroke where it moves down and it intakes fresh air again, and then the process repeats all over again. So we can look at it in another view in this software, and I like it just because I can kind of slow it down so we can see each of these strokes as they are. So that's exhaust, we have intake, compression, and then it sprays the fuel in there, it self-ignites, forces the piston down, and then we exhaust the byproducts again. So again, the process is very similar to that of the gas engine, but you'll see as we look at the property diagrams that it's actually a slightly different process as it's drawn on the PV diagram. So rather than having a constant volume process, we have a constant pressure process from 2 to 3. So this is the PV and the TS diagrams for the diesel cycle. And again, this is an idealized cycle. So if you look from state 1 to state 2, it's an isentropic process, meaning entropy is constant. So it's a reversible process. The same from state 3 to state 4, that it's a reversible process, entropy is constant. So these equivalent processes from 1 to 2 is shown here on a PV diagram as such. And you note from 2 to 3, we have constant pressure, but from 4 to 1, we have a constant volume process. So this is just, again, an idealized model of the actual piston cylinder device. It's very difficult in practice to have a constant volume piece of a compression process, but that's how we exhaust the gases. We're imagining that there's a Q out at a constant volume process, even though in reality that piston is moving up in order to exhaust out the gases. But again, this is just the model and it closely approximates the real life cycle. So if we want to look at our Q in, we have H3 minus H2, but Q out is U4 minus U1. Can anybody tell me or hypothesize why, when we're looking at Q in, we have enthalpy terms, but for Q out, we have just internal energy terms? And if we remember back to the Otto cycle, it's very similar to the diesel cycle, except that we have now, for the Otto cycle, this from 2 to 3 is a constant volume process. Okay, so that's the difference between the diesel cycle and the Otto cycle, is this 2 to 3 process. So why is it now enthalpy terms coming into our equation here, whereas before we just had internal energy?
Because the specific volume is changing?
Yes. Okay, so when the volume changes, what type of energy interactions do we need to look for? So in addition to heat coming in, what's happening at that point, at that from 2 to 3, during that process, that section of the cycle?
Expansion.
Expansion. Okay, so when we have heat plus expansion, we have this boundary work term that combines with our heat term to give us an enthalpy. Okay, so if you remember from before, there's no marker in here, write it up here. H is equal to U plus PV. So from state 2 to state 3, we have a change in internal energy, but we also have an increase in volume. So there's some work being done in the system that's just the system itself moving, right, or expanding. So instead of looking at it in terms of just the internal energy from U3 to U1, from 2 to 3, we have U3 minus U2. We would also have this pressure term times V3 minus V2. So that combines there into an enthalpy term.
So why do we idealize the diesel cycle as a constant pressure with a changing volume process, but the Otto cycle as a constant volume with a changing pressure?
Yeah, so it has to do with spark ignition versus compression ignition. So in this case, we're imagining that this heat input process is because we're compressing that cylinder, and then we all of a sudden have this heat input from the self-ignition. Whereas with the spark, we imagine that we compress the cylinder, then we spark it, and then it forces itself down. So it's the difference between the compression ignition and the the spark ignition, that it's modeled just slightly differently. Yes?
This is a very dumb question, but like, the path of 1, 2, 3, 4,
Yes.
is that saying the path of the cylinder as it goes through?
It's the property value. So at this point, we have a P and a V here. At this point, our pressure and volume's here, here, and here. So it's not necessarily like we're looking at where that piston cylinder device is moving, but by looking at the property diagram, we can say, okay, I know that from state 1 to state 2, my volume is decreasing. So that's a compression process. And from 2 to 3, my volume is increasing. That's an expansion process. Then it expands further from 3 to 4, and then from 4 to 1, it's a constant volume process. It's modeled that way. So the property diagram isn't necessarily prescribing the motion of the cylinder, but it tells us what's happening to the system as a whole. So is pressure increasing or decreasing? Is volume increasing or decreasing? And then these additional cues, like this section from 1 to 2 is isentropic, from 3 to 4 is also isentropic. So PV diagram gives us a nice picture, but we can get sometimes even a better picture by also looking at the TS diagram, so we can see what's happening to temperature during that process as well. So we can see that from state 1 to 2, the temperature is increasing, 3 to 4 is decreasing. Meanwhile, the entropy is being held constant.
So like from like 4 to 1, that's not like the power stroke where it explodes and
The power stroke is here, 3 to 4, for a diesel engine. So it's kind of 2 to 3 and 3 to 4, but
Q out would be the exhaust gas.
yeah, Q out is like the exhaust, and then this 3 to 4 is where you get kind of like a work output. So you just imagine the volume is increasing, right, from 3 to 4. When our piston is expanding, and in this case we're expanding in an isentropic way, that's where we get kind of like our power output of this. Yes.
On the spark ignition, we're assuming that the burning takes place entirely when the piston is at top dead center and not moving at all.
Yeah.
Whereas this one, we're
burning
accounting
in.
for some expansion during the burn and then the remaining expansion.
Yeah, that's kind of how it's modeled. And if you look at the actual property diagrams of those two different cycles, they look different as well. So if you were to, have thermocouples and pressure monitors and everything inside the cylinder as the two different processes were occurring, then they look different. And so this is just the best approximation of how to analyze it, model it, and give it for individual states, because really it's a very curvy process. There's not distinct corners where it turns like that. Okay. Any other questions on property diagrams or these? Okay. So when you're looking at the diesel cycle versus the Otto cycle, it's important to remember this, that H3 minus H2, because it's not a constant volume process, it's a constant pressure process. So we do have some boundary work there that we're accounting for. And if we want to calculate our thermal efficiency, it's the same as before, 1 minus Q out over Q in. And if we assume constant specific heats, then we can change that to be in terms of specific heat and temperature. Okay, in your homework and in the example that we do today, we're going to assume variable specific heats, which means we have to use the property tables instead. And those problems take a little bit longer because there's a lot of interpolation involved, but I'll show you how to do that, and then it should help you a lot on your homework. And then for the diesel engine, we have this thermal efficiency term that's in terms of the compression ratio, R, which is V1 over V2 over V1, V1 over V2. And then the cutoff ratio, which is V3 over V2. So we can rewrite the thermal efficiency in terms of the cutoff ratio and the compression ratio. And this is nice because it allows us to compare how changing the cutoff ratio or changing the compression ratio affect our thermal efficiency, just by putting in those numbers, without specifically knowing necessarily cylinder volumes or temperatures or anything like that. All we need to know is to compare systems is their cutoff and compression ratios, so that we can look at them that way. So how do we increase the efficiency? similar to the auto cycle, that we can increase the compression ratio. And for the diesel cycle, we can really increase the compression ratios a lot more than we can with the auto cycle, because our fuel is not in the cylinder as we're compressing it. The fuel's sprayed in almost or at top dead center so that the combustion occurs instantaneously at that point. So we can keep increasing the compression ratio, but then we have limited returns. So we get to a certain point where we have these really high compression ratios, but we're not getting all that much more out of our system by continuing to increase that. And then, of course, you're limited by the size of your pistons that you want to put in whatever engine you're creating. You can make them super huge and have very long travel, but at some point it becomes ridiculous. Another thing to do is to decrease the cutoff ratio. And if we decrease it to the point where it is 1, if we go back to this equation, where if our cutoff ratio is 1, then this bottom part of the equation kind of explodes, and then this goes to 0. So we 0 over 0, it ends up that term goes away, and you can prove it mathematically, but we're not going to go through that process today. So for a cutoff ratio of 1, we'll have the same thermal efficiency as the auto cycle. So let's look at them again. If we compare those thermal efficiencies, for the same compression ratio, the auto cycle is going to have a higher thermal efficiency. Okay, so why do we get better gas mileage out of diesel vehicles if auto or gasoline engines are more efficient?
Energy content of fuel?
Energy content of the fuel, that's part of it, because we can change the K values of the diesel engine. But the bigger issue is that we can just continue to increase the compression ratio. So even though the diesel engines are less efficient, we can operate at much higher compression ratios. So for the same compression ratio, a gas engine will have greater efficiency. But for higher compression ratios, then the diesel engines perform better. Okay, so that's an advantage there. And then again, where the cutoff ratio goes to 1, the efficiencies of the auto cycle and the diesel cycle will be the same. So in general, we can operate diesel engines at a higher compression ratio because it's compression ignition. We cannot do that with spark ignition vehicles because the fuel will self-ignite, and that's kind of a problem. And diesel engines also usually operate at a lower RPM than gas engines, which is nice because we get greater torque out of the engine. So this is used for trucks, for ships, for trains. Most of those large, slow-moving, high-power vehicles or transportation systems operate with diesel engines. And they have higher stoichiometric ratios, which means that there's a greater air content in the fuel mixed with the fuel, so it's a cleaner burn. So diesel engines actually burn cleaner most often, more times than gas engines, unless it's Volkswagen and you're fudging your numbers for emissions. But
that's recent. That's only recent.
yeah. So there are great advantages to moving to diesel. In the U.S., diesel happens to be more expensive than gas, but in a lot of the countries outside the U.S., diesel is still cheaper. It used to be cheaper, but I think the tax on it in the U.S. is so much higher than it is in some of the other countries, so that it's more expensive to purchase diesel, even if you get greater fuel content. Yes.
So you said that the diesel is cleaner burning. You know how diesel trucks have the emissions? Well, they have emissions, like they take the exhaust and recycle it.
Yeah.
Why do they recycle it if it's burning cleaner?
Well, they probably aren't operating with a high air-to-fuel mix. So for like diesel performance vehicles we're talking about, then they have very high stoichiometric ratios and they can burn clean. So there is the ability for a diesel engine to intake more air. But like for large trucks and ships and boats, they're not trying to move fast. They're trying to move a lot of weight. So because they're operating at the lower RPM and the higher torque, they're not intaking as much air into the fuel mixture, and so it's...
Because they're getting more power out of it.
Yeah, they're getting more power out of it, less speed, and sometimes at the sacrifice of emissions. So it has the potential to be cleaner burning. And there are diesel cars that get like 90 to 100 miles per gallon. We don't, I think, have any in the US.
Motorcycles.
Motorcycle, well, that's a two-stroke engine, so that's a different issue altogether, but, yeah, so, I mean, it's something to think about in engineering design. So let's do an example with a diesel engine, and I'm gonna see if I can get this pen to not freak out on me. So we have an air standard diesel cycle, so air standard, what does that mean? What does that tell us?
Follow those four assumptions.
Yeah, so we follow the assumptions of the air standard cycle, meaning that even though it's an air-fuel mixture, we're going to assume that air is our working fluid, that it's at room temperature. Well, that's not part of the assumptions, but that it's in a continuous loop, and we can assume constant specific heats in some cases, but in this problem we have to assume variable specific heats. So the diesel cycle has a compression ratio of 18.2. Air is at 120 Fahrenheit and 14.7 psia. Dang it, it's in English units. Just kidding. At the beginning, O, the compression process, and at 3200 Rankine at the end of the heat addition process. Accounting for the variation of specific heats with temperature, so that means you have to use your tables. Determine the cutoff ratio, the heat rejection per unit mass, and the thermal efficiency. Okay, so let's set up this problem and let's first figure out what it's even indicating or talking about. So at the beginning of the compression process, air is at 120 Fahrenheit and 14.7 psia. So what is the beginning of the compression process?
Three.
That would be expansion, right? So the volume is increasing, that would be an expansion process. So 1. Okay, so sometimes when you read these problems, you have to read into them because they're not going to necessarily say at state 1. It may say at the beginning of the compression process or at the end of the compression process. So you have to know what that means. What is the compression process? So we're at 120 degrees Fahrenheit and 14.7 psia at state 1. And then 3200 Rankine at the end of the heat addition process. So where would that be? State 3. Okay, so 3200 Rankine. Okay, now we have to be careful because this is given to us in Fahrenheit and that's given us in Rankine. And which unit system do we want to be working in? Rankine, right? So we're going to have to convert 120 Fahrenheit is 579.67 Rankine. And if you want to make your life a lot easier, you could just say that's about 580 Rankine. Then you have like a few less interpolations to do. But I did it at 579.67 and I've already done the math, so there you go. Okay, so when we approach these problems, it's sometimes difficult because there's a lot of different things that we're trying to find. The cutoff ratio. What is the cutoff ratio? It's the ratio of the volume at the beginning or at the end of the compression process to the volume at the beginning of the compression process for heat addition. So this cutoff ratio is V3 over V2 is the cutoff ratio. So we're going to need to find the specific volume at state 3 and the specific volume at state 2. Okay, we don't know either of those things. B, the heat rejection per unit mass. Man, there's a lot of typos in this. Who wrote this? Okay, so heat rejection is what? Q in or Q out? Q out. And how would we rewrite Q out? U what?
U4 minus U1.
U4 minus U1. Okay. Heat rejection per unit mass. And C, the thermal efficiency. And the thermal efficiency is equal to what?
Or work out over
work out over Q in, or 1 minus Q in over Q out. Okay, so as we go through this process, we're going to need to find a couple of different pieces. So we have to figure out, some specific volumes. We're going to need to know some temperatures so we can look up internal energies. We're going to need to be able to calculate this Q in, which is H3 minus H2, right? So
Is it not Q out over Q in?
1 minus Q out over Q in. Yes. Because work out is Q in minus Q out. Yes. So I can actually erase that. So you can read it. Okay. So 1 minus Q out over Q in. Because Q out is less than Q in. So we would have a term that's less than 1, otherwise we get a negative efficiency. Okay. All right, so let's get started on this. And I put in a blank slide so I don't have to go to that crazy notebook and then not be able to get back. So process 1 to 2 is isentropic. And we know that for an isentropic process with an ideal gas, V1 over V2 is equal to VR1 over VR2, or the reduced specific volume. If we go to table A17 in the back of the book, we find that for our ideal gases, we don't have specific volume in the table. And why is it not tabulated in these tables? We instead have this VR term. So why don't we have a table for temperature and specific volume? What are we missing? Pressure, right? So specific volume is not constant with temperature. It changes based on the pressure. Internal energy and enthalpy are a function of temperature only for an ideal gas, but specific volume is a function of temperature and pressure. So we cannot plot it on these tables unless we had tables in terms of temperature and pressure. But we can use these reduced specific volumes in order to help us out. So V1 over V2 is equal to VR1 over VR2. So we can solve for VR2 is equal to V2 over V1 times VR1. And this V2 over V1 is the inverse of the compression ratio, V1 over V2. So 1 over 18.2 multiplied by VR1. And I guess I should write these down over here. So state 1, we have T is 120 degrees Fahrenheit, is 579.67 Rankine. And then we look up our VR1 is 120.88, and I looked up internal energy at 1 because I'll need that later, is 98.84 BTUs per pound mass. Okay, so we plug in this VR1, we get 120.88 divided by 18.2. We find that our VR2 is 6.64. So let's write down state 2. We found VR2 is 6.64. So then we go back to table A17 and we look into this column to figure out where is VR equal to 6.64. And it looks like it occurs between 1520 and 1540 Rankine. Oh no, sorry. I'm on the wrong table. A17E. So 6.64 occurs between 1700 and 1750 Rankine. Okay, so if we interpolate, which we've already done, we find that our temperature 2 is equal to 1725 Rankine, And then while I'm there, I'm just going to look up U2 and H2 as 311.12 kilojoule, BTUs per pound mass. Oh, stupid units. Okay. And then 429.56 BTUs per pound mass.
So you find the T2 based off of what?
VR2.
So,
Yeah, so if you look on the table, it occurs between 1700 and 1750 ranking. So we find where VR2 is equal to 6.64, we interpolate between those two lines on the table to back out the temperature. So that's how we find the second state for an ideal gas, when we know the ratio of volumes.
so 1725 is an interpolated value?
Yeah.
It's just not halfway between?
Well, it ends up being halfway
Well,
between.
yeah, I'm just saying, you just don't assume it's,
No, you don't just
halfway
assume
between.
halfway. Yeah, I actually interpolated it, and
Okay.
that's the value that it came out to be, because 6.64 is in between 6.35 and 6.92.
okay.
Okay, so we have determined our properties at state 2, and then process 2 to 3 is a constant pressure process. So for a closed cycle with the same mass, M2 equals M3, or in other words, PV3 over T3, P3V3 T3 over is equal to P2 V2 over T2. Because P3 is equal to P2, we can cancel those out of the equation. And we find that V3 over V2, or in other words, the cutoff ratio, is equal to the ratio of temperatures T3 over T2. We were given T3 initially, so I might as well write that one down, state 3. T3 is equal to 3200 Rankine. So we have 3200 Rankine divided by T2, which is 1725 Rankine. So we find that our R sub C is equal to 1.86. Was R sub C. Okay, so that's part A of the problem, the cutoff ratio, which is the ratio of V3 over V2. So we first needed to find state 2 by comparing the volume of state 1 and state 2 and using the table to find that second temperature. Then we were able to find state 3 using this M2 equals M3. We knew already the temperature of state 3, and we were able to find that volume ratio, or the R sub C. Okay, so for part B, we want to find Q out, which is equal to U4 minus U1. We know U1, we don't know U4. So we have to figure out how to find that Q out term. We know that from state 3 to 4, we again have isentropic expansion. Okay, or it's an isentropic process, meaning S is constant. So again, we can say VR4 over VR3. I'm going to write this one down, VR2. Already did. Okay. VR4 over VR3 is equal to V4 over V3. Now, I know the temperature of state 3. I can automatically look up VR3. And by interpolation, it is some value. 0.955. Okay, so again, we have these ratios. But this time it's a little bit tricky because V4 over V3 is not a known ratio. It's not the compression ratio, it's not the cutoff ratio. But we know that V4 is the same volume as V1 for a diesel cycle. So if we look back at our picture, V4 and V1 are the same volume. then we know that V3 is equal to 1.86 times V2. So we can plug those two in there. So VR4 is equal to V1 over 1.86 V2 multiplied by VR3. So now we see something familiar, this V1 over V2, which is our compression ratio. So we can rewrite this, that VR4 is equal to the VR3 times R over RC, or this 1.86. So we find the values for that, 0.955 multiplied by 18.2 over 1.86. So we find 9.345 for state 4. Okay, so we don't know T4, we do know VR4 is 9.345. So we go back to the table and we look up to figure out where does T equal this, the value that gives us a VR of 9.345, and we find that T4 is 1533.55 Rankine. While we're there, we're also going to look up U4, which is 272.93 BTUs per pound mass. So we find we now have our U4 and we now have our U1. So we can go back to this equation and find that Q out is equal to U4 minus U1 is Q out. So Q out is equal to 272.93 minus U1, which is 98.4 BTUs per pound mass. So Q out is equal to 174.09 BTUs per pound mass. So that's part B. So for part C now, we're trying to find the thermal efficiency, which is equal to 1 minus Q out over Q in. We know Q out, Q in is equal to H3 minus H2. So H3 is specified, we can look that one up, and we find it to be 849.48 BTUs per pound mass. So we can plug in the numbers for that, and we find that Qn is equal to 419.92 BTUs per pound mass. So our thermal efficiency, 1 minus Q out over Qn, plug in the numbers, and we get 0.585 or 58.5%. So you can see how there's several steps involved just in finding the property values of these problems. So if you know the cutoff ratio or you know the compression ratio, then you know the ratios of the volumes. So we never explicitly solve for specific volume in this problem. We just use the ratios. So you don't have to necessarily solve for specific volume. If you know the ratios, then you can find a state that's a parallel state or concurrent state. Okay. Any questions on this example? So this one's very similar to your homework. Hopefully you understood it and can follow along. There are some diesel engines that the fuel is injected sooner than previous models, so this combustion begins while it's still being compressed. And so we look at it as a combination of a constant volume and a constant pressure process. So the heat addition has to be modeled slightly differently. This is maybe perhaps more accurate when we're looking at some of the higher performance diesel engines, but we don't necessarily need to do the analysis of that. So you would have to look at it from state 1 to 2, and then we call this like a state 2A, because from 2 to 2A and 2A to 3 is not a straight line. It bends that corner if we wanted to do the analysis of that. Okay, so there's a lot of interesting stuff, and this was actually sent to me by Kane West, that the Mazda Skyactiv X, which is kind of like, it's kind of like they're trying to find a hybrid between a gas and a diesel engine. So Mazda's been working on these Skyactiv engines. So they have a Skyactiv G and a Skyactiv D, which are their gas and their diesel engines respectively. And so they've been playing around with some of the parameters that allows for greater thermal efficiency within the engines. So changing compression ratios, specific heat ratios, how long the combustion happens, the timing of the combustion, heat transfer that occurs within the cylinder to the walls of the cylinder, the pressure differentials between the inlet and the exhaust, and then any mechanical friction. So their goal is to turn all of these boxes green. So by getting it closer and closer to a reversible or an ideal state, then they're able to improve the efficiency of these engines, get higher performance, greater fuel economy, and it's an interesting process. So what they're doing with these new diesel engines is that they have a very lean air-to-fuel mixture, and they have a slight delay in igniting the fuel. So it's almost like a spark ignition, compression ignition mixture, because they're sparking to ignite like this little ball of gas here that's not gasoline, not diesel. It's like sometimes argon or some other gas. They try to ignite this little ball, which creates this little fire, and then the fire ignites everything else. So it's kind of an interesting way of doing it, and there's a pretty in-depth article on the analysis of it that talks about what they're doing, how they're doing it, what they've changed from previous models, and how these vehicles perform, because they do actually have like a prototype concept car that they've made and people have driven, and it's pretty interesting. So
this diagram is saying that there's additional compression, so there's compression from the piston, and then the little argon explosion, like you're saying, causes...
Yeah, so they're having compression ignition and
so
spark ignition also.
Battling compression.
Yeah, so it's...
equates to a higher compression.
Yeah, so I guess it's a more complete burn, but they also get... So some of the disadvantage of waiting for the piston to be fully up before you have your compression ignition occur is that, yes, your power stroke is longer, but sometimes it's not easy to time so much as when you have a spark ignition. And so there's some of the variables that they're playing with for the combustion period and the power stroke length. By allowing it to have a combustion ignition plus a spark ignition, you kind of get the best of both worlds in that way. So it's pretty interesting if you want to go look at it. And then there's some that we looked at a little bit last semester. So like a Wankel engine it's not a 2-stroke or a 4-stroke, it's some kind of a circular stroke where the intake and the exhaust are being similar to a 2-stroke engine where the device that's moving up, I don't necessarily want to call it a piston, it's more like a can, but is covering and uncovering the intake and the exhaust. So it's kind of interesting. They have a lot of reliability issues with it, as you can imagine, for something that's an off-centered rotation, but any slight irregularity in that causes significant vibration, and then it vibrates itself apart. And then like the omnivore engine, where it's another concept engine where you can change the amount of like your ethanol and gasoline mixture, you can change your air-fuel mixture, you can change the size of the cylinders so that you can have a higher compression ratio temporarily. And this was developed by Lotus, and I'm not certain if they do have actual working prototypes or not, but it's another kind of interesting idea to think about to improve the efficiency and the performance of an engine. And then there's hybrid engines. So the Prius, for example, is a hybrid where they have a gas engine as well as an electric motor. And so the Prius can receive its power from the electric motor, or it can receive its power from the gas engine, or it can have the gas engine charging the electric motor, or it can have both of them on simultaneously when it needs more power. And so it uses this planetary gear system because it allows gears that were inputs to then become outputs, depending on which direction you want the energy to be transferred. So it's completely different than, it's a completely different transference of power than you would see in a typical just engine piston with crankshafts attached to other things, because you have the electric motor directly driving the wheels at times, and then at other times the engine is driving it. So, okay, so that's our end of our discussion on the diesel cycle. We're now going to talk about Stirling and Ericsson. And these are two cycles that are totally reversible. So just like the Carnot cycle, they're idealized, very idealized models that are difficult to achieve in practice with real machines. But because it's a reversible model, it's another thing that we can study and see how we can approximate it and try to get there so that we get better efficiencies. So from state 1 to 2 is an isothermal expansion, so a constant temperature expansion process where we have some heat input. And then from 2 to 3 is a constant volume or isometric regeneration process. So the volume is constant, and as we're expanding, we're removing some of the heat from this, this fluid, and we're transferring it to the fluid on the opposite side of the cycle. So then from 3 to 4 is a constant temperature, isothermal compression, and then from 4 to 1 is again, an isometric regeneration process, where now we're receiving some heat from the fluid on the other side in order to preheat our gas as it's going into this cycle here, or this portion of the cycle. So regeneration, we'll learn a lot more about this on Thursday when we talk about the Brayton cycle. But it's a way of using some of the energy that's already within your system. You know, for example, sometimes we have to heat things up and then cool them down. Well, as we're cooling something down, if we can remove some of that heat and use it to preheat a fluid on the other side of our system, that's a positive use of the energy rather than just depositing it into the environment. So we can't use it to completely heat our fluid, but we can use it to get a preheat, and they do often do that and employ that in industry. So let's work through an example of the Stirling cycle, because I think it's a little bit more informative and helps us understand the components of it and how to analyze it. So we have an ideal Stirling cycle using helium as the working fluid, and it operates between the temperature limits of 300 and 2000 Kelvin, and the pressure limits of 150 kilopascals and 3 megapascals. So if we were to draw that on this diagram, so our T sub L is 300, our T sub H is 2000, and then our high pressure would be here at state 1 of 3 megapascals, and our low pressure would be here at state 3 of 300 kilopascals. Okay, so again, this is another example of reading the problem and knowing and understanding where those values are assigned in our cycle. So our pressure limits and our temperature limits. It's not, you know, P1 and P2, it's P1 and P3, so we have to know that. So assuming the mass of the helium in the cycle is 0.12 kilograms, determine the thermal efficiency, the amount of heat transfer in the regenerator, and the work output per cycle. Now, because this is a totally reversible cycle, the thermal efficiency is equal to 1 minus T sub L over T sub H. Okay, because the Carnot principle, one of the Carnot principles is that the Carnot cycle will have the greatest, or a reversible cycle will have the greatest thermal efficiency of any device. The second Carnot principle is that any reversible device operating between the same two temperature limits will have the same efficiency. So even though this is not operating on the Carnot cycle, because it's also a totally reversible device, at best it will have the same efficiency as the Carnot cycle. So any totally reversible device will have the same efficiency between the same two temperature limits. So even though it's not Carnot, it still has the same efficiency. So 1 minus T sub L over T sub H, that's pretty easy. We're already given our temperatures in terms of Kelvin. So just 1 minus 300 Kelvin over 2,000 Kelvin, which gives us an efficiency of 85%. Okay, so then part B, the amount of heat transfer in the regenerator. Okay, so this regeneration process happens between 2 to 3. So we have some heat out, Q out from 2 to 3, which will be equal to Q in from 4 to 1. So if we want to calculate the heat in or the heat out for either one of those cycles, because we're assuming constant specific heats with helium, I guess we didn't say we're assuming that, but I'm going to say assume constant C sub P, C sub B, because it didn't tell us to do otherwise. So our Q in is equal to C sub V times T1 minus T4. So we're given already T1 and T4. C sub V for helium is 3.1156 kilojoules per kilogram Kelvin. T1 minus T4 is 2,000 minus 300 Kelvin. And this gives us a lowercase q. If we want to find a big Q, it has to be multiplied by the mass, so 0.12 kilograms. So Q regen in is equal to 635.6 kilojoules.
What's that little part you squeezed in there, 0.1?
This 0.12 kilograms is the mass.
And we were given the CV,
CV, we can just look up in the book, table A1.
which is all the same.
Yeah, table A1. So 2,000 minus 300 multiplied by this 3.1156 multiplied by the mass, we get 635.6 kilojoules.
In this example, is it assuming that all of the heat in required comes from the regeneration process?
All of the heat that comes in during this session. So there's this Q in is different than the Q of the regenerator. So there's some Q coming out from 2 to 3 and it's going directly in Q 1 to 4 because it's an idealized reversible process. But this Q in and this Q out are not from the regeneration components. Okay, but we're asked specifically to find the amount of heat transfer in the regenerator. So that would be from 2 to 3 to 4 to 1. Thanks for that question, that was good to clarify. Okay, so then our thermal efficiency is equal to work out over Q in. So our work out is equal to the thermal efficiency, which we solved for earlier, multiplied by Q in. And again, this Q in is not the same as the Q regenerate. Does not equal that. It's a different Q in because it's the area under the curve on a TS diagram from state 1 to state 2. Okay, so we want to find Q in, it's going to be this area, which fortunately for us is a rectangle, so we can calculate it algebraically. So Q in is going to be the mass, well, Q, sorry, big Q. Q in is going to be the mass times the high temperature times S2 minus S1. Okay, so now we have helium, which is an ideal gas. We have entropy that we're supposed to calculate. We don't have a table that gives us entropy in helium, but we do have some equations called the Gibbs equations, which allow us to calculate that. So S2 minus S1 is equal to C sub V, natural log of T2 over T1, plus R, natural log of V2 over V1. So again, this comes from the Gibbs equations. I don't know if this is first or second. I think it's the first. That doesn't really matter. Okay, so T2 is equal to what? Let's look back at our picture. TH. What's T1? Also TH. What's the natural log of 1? 0. So this part goes to 0. So we just have our natural log of V2 over V1. Okay, do we know V2 over V1? Do we have a compression ratio for this problem? No, we have this V2 here, which will be that value, V1 here, which will be some value. We know that V1 is the same as V4, and that V2 is the same as V3, but we don't know V2 over V1. Okay, so that's a minor hiccup, but we know that V2 is the same as V3, so it's equal to V3 over V1. Okay, so then we can say, from the ideal gas law, PV equals RT. We can rewrite this. V3 is equal to RT3 over P3, and V1 is equal to RT1 over P1. So we get rid of the R, that cancels out. We have P1 T3 over P3 T1. Okay, because we know P1 and P3. So if we look back to this picture, the pressure is given as 150 and 3 megapascals. That's P1 and P3. We don't know P2, we don't know P4. Turns out we don't need them because we know the ratio is the same between V2 over V1 or V3 over V1. So that's the reason that we did that substitution, to have it in terms of T3 and T1 instead of V2 and V1. So if we put in the numbers and solve for that, we have S2 minus S1 is equal to R, natural log of P1 T3 over P3 T1, and we get that as equal to 2.28 kilojoules per kilogram Kelvin. So then Qin is equal to M times TH times S2 minus S1. So it's equal to 0.12 kilograms multiplied by 2000 Kelvin times 2.28 kilojoules per kilogram Kelvin. So Qin is equal to 547.2 kilojoules. What we're actually trying to solve is work out, if you remember, the thermal efficiency times Qin. So we have 0.85 multiplied by this 547.2 kilojoules gives us 465.12 kilojoules. Okay, so the trickiest part of these problems is when you have volume ratios and you have to try to be, you have to finesse it in order to find a ratio that you know and substitute it in for the one that you don't know. Or maybe have it in terms of temperature instead of temperature and pressure instead of volumes. So sometimes you have to play around with it. You have to look at what you're given in the problem, what you actually know, and then try to find some of these other things out. Okay. So regeneration, both the Stirling and the Ericsson cycles utilize this regeneration, and so we transfer heat from one side of the process, or from one component of the process, to sometimes it's to a thermal storage device, and then that acts as a heat exchanger as the fluid is coming through from the other part of the process. So it's borrowing energy from one place and using it in another part of the process. And regeneration serves to increase overall efficiency because it's not free energy necessarily, like it's coming from nowhere, but it's energy that would otherwise be expended that we're kind of like recycling and reusing within our process to help heat things up. Okay, so it only works when you're trying to heat something up. You can't use regeneration in any other ways to get like a greater work output or directly. It's meant to just preheat things or add heat. So if we look at the two different cycles, the Stirling cycle and the Ericsson cycle, we have this sort of a comparison of their thermal efficiencies. It's equivalent to the Carnot cycle. And the Stirling cycle is really quite difficult to achieve in process in real life, but a simplified model would be a piston cylinder device with a regenerator in it. So you have some heat that's being stored in that regenerator and then it comes back out and you're able to use it for the later parts of the process. And the Ericsson engine, although it's the ideal model and it's not often implemented, the concepts are used quite often in steam power plants and in like gas turbine cycles or Brayton cycle. That is very similar to the Ericsson cycle, though it's not a reversible version or a reversible cycle. So let's do an example with the Ericsson cycle now, which is similar analysis, similar methodology as we have used thus far for the gas power cycles. And again, relying upon our knowledge of entropy equations for ideal gas and how to make these ratios work in our favor. So we have an ideal Ericsson cycle with air as the working fluid in a steady flow system. Air is at 27 Celsius and 120 kilopascals at the beginning of the isothermal compression process, during which 150 kilojoules per kilogram of heat is rejected. Heat transfer to the air occurs at 1200 K. Determine the max pressure, the network output, and the thermal efficiency. Okay, so again, let's try to define what's happening. So what is the beginning of the isothermal compression process? What state is that? State 3. So from 3 to 2 is isothermal compression. And how do you know it's compression? 3 to 4. Isothermal compression. So you know it's either 3 to 4 or 1 to 2, right? And in this case, if we look at our PV diagram, 3 is a higher volume than 4, so we know that's compression. So state 3 to 4 is isothermal compression. And the beginning of the isothermal compression process would be state 3. So it's 27 Celsius and 120 kilopascals at state 3. Okay, during which 150 kilojoules per kilogram of heat is rejected. So our Q out is 150 kilojoules per kilogram. And then heat transfer to the air occurs at 1200 K. So what is that talking about?
Just the regeneration part?
It is not the regeneration part. That was a good guess.
The temperature at which compression takes place?
Heat transfer to the air occurs at 1200
Is that Q?
Kelvin. When are we having a Q in? Yeah.
1?
Okay, between 1 and 2. So this T sub H is equal to 1200 Kelvin. And we know that we kind of know that it's this Q in that they're talking about and not the regeneration process because it's talking about heat transfer and not regeneration. So generally, if they're talking about any heat transfer during the regeneration process, they explicitly say that. So if they're just saying heat is transferred in, then. Okay, so determine the max pressure in the cycle, the network output per unit mass, and the thermal efficiency. Where is the maximum pressure going to occur? Yeah, so this is going to be Pmax. Will be either P4 or P1. One of those may be easier to find than the other. net work output is going to be equal to what? Work out is going to be equal to Q in minus Q out. And the thermal efficiency is equal to 1 minus T sub L over T sub H. Okay, so let's start plugging through it. We know that we need to find the max pressure, and it's either in state 1 or state 4. Let's just go ahead and look at state 4. Okay, so this is kind of a roundabout way of getting pressure, but we know that S4 minus S3 is equal to C sub P natural log of T4 over T3. This is the second Gibbs equation, minus R natural log of P4 over P3. Okay, so we now have P4 in our equation, and we already know P3. So that's a good thing. T4 and T3 are the same temperature, so that term goes away, because natural log of 1 equals 0. So we have S4 minus S3 is equal to R minus R natural log of P4 over P3. So P4 is an unknown, but so are S4 and S3. We also know on a TS diagram that the area under a curve, I'm going to clean this up just a little bit, the area under the curve on a TS diagram is the heat transfer. So Q out is going to be equal to is equal to T naught times S4 minus S3. And this is actually negative Q out is equal to T naught times S4 minus S3. So we can rearrange this in terms of S4 minus S3 is equal to negative Q out over T naught. So now we can set this equal to this, because we know Q out, we know P3, we know R. All we have unknown is a P4 in our equation. So negative R natural log of P4 over P3 is equal to a negative Q out over a T naught. And T naught is just the temperature at which that heat transfer is occurring, so it's T sub L. So we can solve for P4 is equal to the exponential of Q out over T sub L times R multiplied by P3. P3 is not in the denominator, it's just squished.
What is the TO? Is that just
T sub O is the temperature at which the heat transfer occurs. So Q out is occurring at T sub L.
okay?
Yeah, so T naught is equal to T sub L.
And I know it says it's isothermal, but how else would you get the Q out? Like, what would the Q out be?
How
would you even get the Q out if you're not losing any heat? Is that what I'm thinking now?
well, the temperature is isothermal because you're removing heat during the
Okay.
compression process. Yeah, because naturally if you compress a gas, it's going to heat up, or its temperature will increase.
So you're
So you're
losing
removing
the same
heat in
temperature.
order to keep it the same temperature.
Yeah, if the Q out wasn't there, we'd
Right.
go back up.
How does that work?
That's a good observation. Okay, so P4 is equal to the exponent of Q out over T spelled R, multiply that whole thing times P3. Plug in the numbers for that, we get 685.16 kilopascals. So Q out's given in the problem, T sub L is given in the problem, R we look up, and P3 is given in the problem. So we're able to find P4 in terms of all the things that we know. So again, it sometimes requires some manipulation, where you think, okay, I need some equation that has P4 in it. I don't have great tables. Oh, I do have great tables for air. This was human. That was the last problem. Okay. So sometimes you have to play around with it and try to figure out what you know, what you don't know, and then look at other examples of problems where you use these tricks to try to find things. Okay. So part B, work net out is equal to Q in minus Q out. And we know that for reversible cycles, Q sub H over Q sub L is equal to T sub H over T sub L. So in this problem, we're given Q sub L, we know Q sub L, but we don't know Q sub H. So we can solve for Q sub H is equal to T sub H over T sub L times Q sub L. So if we plug in the numbers, 1200 Kelvin over 300 Kelvin, multiplied by 150 kilojoules per kilogram, and we get 600 kilojoules per kilogram. So work out is equal to 600 minus 150 kilojoules per kilogram, which is 150 kilojoules per kilogram. And this is only valid for reversible systems. So for the Stirling cycle, the Ericsson cycle, the Carnot cycle, it's not valid for the Otto cycle or the diesel cycle. Okay, so then the last, thermal efficiency is equal to 1 minus T sub L over T sub H. Plug in the numbers for that, we get 75%. So 300 Kelvin over 1200 Kelvin. Okay, so get started on your homework early, because there's a lot of that stuff, the tricks, the manipulations that maybe you just need. Okay, so just some last additional notes about the cycles. Stirling and Ericsson, they're both difficult to implement in process, though there have been some Stirling engines. And they're both considered external combustion, meaning that rather than having some internal combustion process that delivers our power stroke, we're receiving heat from an external source and using that to drive our cycle. And the advantage of this is that we can use a variety of different fuels. So Stirling and Ericsson cycles are not dependent on any one specific type of fuel, but it does take more time to, it allows more time for complete combustion so that when you're burning these fuels externally just to generate heat, you can burn them completely. You're not just worried about the timing of the device and trying to get that combustion just right. And then regeneration, as we'll see next period, increases efficiency. So it's a great way to improve the efficiency of our cycles without having to redesign everything about our turbines and things like that. So get started on your homework, and I will see you on Thursday.